Hey everybody, welcome back to EM378 SI Online. Just a heads up, we'll do announcements here real quick, or SI stuff as I'll call it. This will be our last video on modeling / dimensional analysis. Going forward, we're going to start pipe flow and whether or not it's laminar or turbulent, stuff like that. So if you're getting comfortable with this stuff, that's good. We'll be moving on here pretty quick though. And then also, again, my usual WebEx plug, right? Mondays at 6, Tuesdays at 6, and then Thursdays at 5. This is a really good time to ask questions, make sure stuff makes sense. Even if you aren't going now, this will be in effect for the rest of the semester. So keep showing up to those. I do have a personal WebEx room that you can find through the SI website. So find link through SI website. Those of you that have already been at these WebEx meetings, thank you so much. It's been a good time. If you haven't been yet, I suggest you go. All right, let's get into the problem. So problem 7.63. So as shown in the figure below, noisemaker B is towed behind a minesweeper A to set off any acoustic mines such as at C. They drew a little mine there. I don't know, it looks like a box. Anyway, drag force on the noisemaker is to be studied in a water tunnel at a quarter scale model. The model is a quarter of the size of the prototype. So that's good to know. The drag force is assumed to be a function of the speed of the ship. So we'll write that real quick. So speed of the ship, the density and viscosity of the fluid, and the diameter of the noisemaker. If the prototype is towing at a speed of 3 meters per second, determine the water velocity in the tunnel for the model tests, and B, if the model tests of part A produced a model drag of 900 newtons, determine the drag expected on the prototype. All right, so first thing we do in all of our dimensional analysis and modeling problems is we establish what variable we're looking at and what it's a function of, and then we take those and we make our dimensionless variables with them. All right, so this should be pretty comfortable by now, hopefully, so I'll move through it pretty quick. Also, a side note, this little fancy capital D, this is how we denote the drag force. That's just kind of convention. We'll see that once we start talking about drag forces, drag coefficients, and lift coefficients towards the end of the semester. So just tuck that in the back of your mind. We notice that we're working in SI here, right? It says meters per second, newtons, so we'll use ml and t. For drag, that is mlt to the negative 2. For velocity, length time to the negative 1. Density, mass, length to the negative 3. Viscosity, ml to the negative 1. T to the negative 1. And then I think that's, diameter of the noisemaker is just L. So we'll need, right, we have 5 variables and also 3 reference dimensions, ml and t, that are used in this case here. So we need 2 pi terms. Not bad. And the other thing that we can notice about this is that, right, we have all of the ingredients for a Reynolds number, right? Rho, V, D, and mu. So we can say for sure one of them is going to be our Reynolds number. Or, sorry, I'm using capital D here. That is going to be pi 1. And the other one that we're going to have is our drag coefficient. I don't think you guys have seen this yet, but again, this will come up later in the semester once we start talking about lift and drag coefficients. And that is just, you can do this by the dimensional analysis with m to the 0, l to the 0, t to the 0, and figure it out that way. But for sake of time, we'll just give it here. Drag 1/2 rho b squared d squared. And that is CD. I already wrote over there. So that's our pi 2. So we have CD is a function of our Reynolds number. All right. So moving on. What we're looking for in part A, or a little A here, if the prototype is towing speed is 3 meters per second, so V equals 3, determine the water velocity in the tunnel for the model tests. So we're looking for our VM. And what we'll assume here is that we're working with the same fluid, which means that rho equals rho m and mu equals mu m. Same densities and same viscosities here between our prototype and our model. And if we look at Reynolds similarity, that means we're going to have our rhos and our mu's are going to cancel out. And like we've seen in a previous problem, we're just going to get this here. And we know from our scale model, which is just 1/4, that dm is, of course, 1/4 of the diameter in our prototype. This means that rearranging this a little bit and plugging in the relationship between dm and d, this just gives us that our Vm is 4 times 3, 12 meters per second. So there's part A. And what you want to ask yourself is, does 12 meters per second make sense for testing velocity of water? And it does. So we're good in that respect. Answer makes sense, and so does the model. All right, part B. If the model test of part A produced a model drag of 900 newtons, determine the drag expected in the prototype. So we're given the drag in the model is 900, and we want to know what the drag in the prototype is. So drag isn't represented in our Reynolds number. However, it is represented in our drag coefficient, so we'll use CD similarity, or drag coefficient similarity. So we have, again, the density is going to be the same between the two, and the 1/2 is going to cancel out because it's on both sides. We'll write that out, though, just to be clear about things. So dm 1/2 rho m Vm squared dm squared 1/2 rho v squared d squared. 1/2 cancels out, rho cancels out. And then we have a V and a Vm from part A, right? Our Vm is 12 and our V is 3. And then if we rearrange our variables a little bit, we'll get as poorly done. We'll try that again. There we go. That's a little better. All right, so the drag that we're looking for is just the drag in the model, velocity over the velocity in the model squared, and then diameter in the model also squared. So we get the drag that we're looking for, move that up a little bit, is just 3/12 squared times this ratio here is still 4, and then the dm that we're given is 900. All right, and so oddly enough, we get that the drag in this case is going to be the same between our prototype and our model. That's because we ended up having the same ratio between our Vm as in our velocity, which is going to be the same in all of our cases, right? So that's pretty convenient. So just something to keep in mind, asking yourself whether or not your answer makes sense and whether or not it makes it a feasible model or not. And something else that I wanted to hit on, the Reynolds number. Why does it keep coming up? Well, that's because it describes fluid flow. It's a dimensionless description of fluid flow that comes up in a lot in these dimensional analyses. And if I get the book here real quick, I'll open up to, well, I gotta find it first. But there are a bunch of dimensionless variables that you're gonna see kind of all over it. So this Reynolds number, right? It's generally of importance in all types of fluid dynamic problems, and it's a ratio of the inertial force versus the viscous force. So that would be pipe flow, right? So keep that in mind. Other variables that come up and might come up also on an exam, like in a multiple choice or something, that he's mentioned. I think if he hasn't mentioned them in his lectures yet, he'll get around to it eventually, or in exam review or something. So ones that I would remember for exams are the Reynolds number, just put a little star by it. Maybe the Froude number. Euler number, probably not. But I wouldn't be surprised if he, like, one thing that he might ask is, what's the interpretation or the ratio of the Reynolds number? And it'd be a multiple choice. And the correct answer would be the inertia force over the viscous force. Or for the Froude number, this is the inertia force over the gravitational force. Cauchy number is the inertia force over the compressibility force. And Mach number, inertia force over compressibility force. So those are a couple other, oh, dang it. Wait, I'll get it. Nailed it. That would be a couple other things to keep an eye out for as you're starting to review a little bit for the exam, or just so you can keep up with how these dimensionless variable problems are going. So Reynolds number, Froude number, Cauchy number, Mach number. And then there's a bunch of others. For example, what we see here at the bottom, if this document camera will agree with me, is this drag coefficient that we saw in an earlier problem. We'll see if that can't focus. Whoop. Yeah, that'll be all right. So here we have that drag coefficient that I was talking about in this previous problem. Drag over 1/2 times rho v squared over L squared. Here our L was a diameter. So yeah, this table is on page 362 if you want to take a look at it. You won't have to know all of them or memorize this or anything, but to be familiar with Reynolds number, Froude number, Cauchy number, Mach number. Yep, all things to keep in mind. With that, hope you guys are having a good week with these online classes. Make sure, again, check in with WebEx. That's always helpful. There's a little smiley face. Hope you guys have a great rest of your week. See you in WebEx.